great. This is good because now we've gone past the hard math part and now we're back into the more fun and interesting parts. Because now we're going to be learning about why the road pieces seem to be speeding up or slowing down depending on what piece we have. And that's going to go and create a different I'm going to have to go and create another diagram, but this one's a lot easier to understand. So I'm going to make a blackboard instead of a whiteboard here. I'm just going to have to delete everything. So close your eyes for just a second. It's so bright. Ah, geez. Hurts my eyes sometimes. There you go. Going to make a blackboard there. Much easier to see. And what I'm going to be creating is something known as instantaneous. I can't spell it. Let's just look at the spelling. Instantaneous velocity. And we also have angular velocity. Have you guys ever heard these terms before? Angular?
I just want to say something else. I found a different problem.
Oh, yeah.
So,
oh, you want to share your screen?
Sorry, excuse me. Yeah, but it's a very random chance.
Oh, okay, let's take a look. Okay, could you describe what might be going on?
Wait, I think, yeah, here. So basically, I noticed on one where I got like perfect left turns, right? That your guy actually moves slightly to the right. Here, I'll share.
Yeah, actually, that is another, that's a more subtle thing that could happen. Yeah, that is another error that we have. Like, so it's a good thing that you pointed that out. Oh, we have that weird pixelated box again.
Wait, can you see it?
I can only see a section of the screen that's a pixelated box.
Oh, okay. Well, basically, yeah, he turned slightly to the right. I didn't really notice it on most of them, but I got a perfect one where it was like all left.
Okay.
Yeah, all left. So, and you can notice. You can notice.
Oh, let me just share a portion of my screen here. But what we're gonna, yeah, that's actually the most subtle bug that we have. We have the more obvious ones where obviously our right pieces are not working as intended. Our left pieces seem to be speeding up and slowing down. But then over the course of some time, if you let it run for a little bit, there's going to be an issue with somehow the robot seems to be moving from the center of the road. There's a little bit of deviation or sliding from the robot here. And that's obviously going to come into, well, that's going to be very drastic when we're trying to dodge obstacles on our road. So we're going to have a little bit of kind of drift on our robot that we're trying to prevent from happening. And it happens over the course of a little bit of time, right? It should be following the dotted line here, but you can see that my robot kind of drifted off to the right, as Thomas mentioned. Yes, that actually does. That's a very subtle bug that if our character's remaining still, we want him to remain still in the center of the road. Right now, there's some drift. If we were to move our character left and right to dodge obstacles, eventually we're going to go into a lane that we can't avoid, and we're going to crash into an obstacle. So there's several things we're going to have to deal with, and we're going to start with the more obvious ones, and then we'll deal with the drift a little bit later. But the most obvious one that we have is how come some pieces in the left, when we turn left, move faster than others? And that has to do with something called instantaneous and angular velocity. Because I don't know if you've noticed, there's actually some really cool things here. This is a physics problem. We have, let's say, we have a circle like so, and then we have, let's say, an inner circle as well. And let's say I have a little inner circle here. So I have a little circle, and I'm going to create a row piece again that's based off of this circle. Let's say I have a row piece that's about this shape. Now, this is my curved row piece, and this is the outer and inner circle. So let's say we have point over here that's A, and we have another point over here that is B. And let's say I can rotate this piece all the way around in 360 degrees. A will follow the inner track, and B would follow the outer track. Right? If we were to rotate this piece completely 360 degrees in a circle, A would follow the inner track, and B would follow the exterior track. But if you guys have noticed, the row piece, this distance between the two remains the same constantly. A and B stay the same distance apart. However, you notice here, what do you guys notice? If A is doing the inner track and B is doing the outer track,
B is moving a lot faster than A.
Yeah, B has to cover a lot more ground to cover the same amount of distance that A has to travel. So technically, point B is going to be moving faster than point A is. They all have what is known as the angular velocity, but they all have a different instantaneous velocity. So angular velocity can be described as angular velocity is, oh, I gotta spell this. Angular velocity is known as how fast, right? How fast a object is rotating around something else. And instantaneous velocity is technically each of these points that we see here, right? B must be moving faster than A in order to stay the same distance apart, right, from A. They never change. So B must be moving faster out on the outside than on the inside. And that's also if you go into, let's say, a one of those thrill rides at, let's say, Canada's Wonderland or some kind of theme park. If you were to go on the outside of the spinning, let's say, like a spinning teacup, you would be moving faster than you would be if you were closer to the wheel in the center. You'll be that because you'll be experiencing more instantaneous velocity than the angular velocity of rotating the from the inside. So that's why whenever you're moving really fast on a roller coaster, or you're using if you have those like thrill rides that have like the spinning wheel, you're moving on the outside much faster than moving the rotation on the inside. So instantaneous velocity is known as how fast a thing would move, or a point, you could say an object would move when it was to let go of from its rotation point around something, right? So around something else. So you can also think of that as, let's say you have a slingshot. How slingshots became so deadly back in the ancient times is you got a very slow rotation of your wrist, right? And there's a huge rope that's obviously swinging the stone in the kind of like satchel that you have to rotate, and you can build up quite a bit of speed and distance with just slightly moving your wrist, because there's so much more rotation in that distance, right? The rope that you has the, let's say, the sling is the same distance apart from, regardless of how far how fast your hand rotates. But as soon as you let go of that and you fling that rock, let's say, towards the enemy, it's going to have a greater instantaneous velocity than what your wrist can even possibly do, right, to rotate that. So it's very interesting that, yeah, even though B and A are the same distance apart, B is moving much faster than A is in terms of the distance that obviously it has to cover in the same amount of time, and the speed at which it needs to, if it were to propel off. So obviously, depending on the curved piece that we have, if it's moving at, let's say, 15 degrees or 40 degrees, that changes the angle of our rotation point, and therefore the piece moves faster or slower. It's kind of interesting, right? So B is moving much faster than A is. And that's what we have to kind of fix. We need to make sure we're going to be calculating the angular velocity and not use the instantaneous one, which is what we're using right now. Does that make sense before we go any further? Do you have any questions, or does that kind of explain what's going on a little bit better? I don't know. If you don't know, have any questions, but you're confused, let me know as well.